Hey everyone, my name is Brent Langston. I'm a developer advocate for Amazon Web Services, and this talk is about moving from a monolith to microservices and all the bumps along the way, all the problems that you might experience, all the things that you might encounter that you're going to have to figure out how to solve. Before Amazon, I worked for a little startup called Cloud Passage and helped re-architect their platform from monolith to microservice. So I've been where you're at. I understand what you're going through or are about to go through. So I'm definitely able to sort of talk you through it. At the end of all of this or later, if you have any questions, definitely track me down. I'll be around at reInvent the whole time, and then of course you can hit me up on Twitter with any of the questions that you might think of later. But for now, let's talk about what it is that you're going to have to figure out. What are the things that you're going to have to solve for? Anytime you try and make a change of this size, it's good to think about all of the different aspects of that change and how it's going to affect your organization. So let's start off by looking at just sort of categories of change. Everyone always jumps to technical. How am I going to solve this problem technically? But really, you're almost doomed if you don't also solve for the problem of convincing people that are involved and being able to have an effective workflow figured out. So we need to have ready solutions to solve for that as well. So let's take a look. What are some of the problems that you might encounter that fall more into the people category? What are some hurdles that you'll have to prepare for? Well, we often will hear, well, I'm used to doing it this way. And you're going to come along and try and introduce a new way of doing things. So that in and of itself is going to be an obstacle that you're going to need to be prepared for. Why is the new way better? What is going to be better for the developer or for the product person or for whoever the team member is? Just be ready to answer, why is this way better? One specific question that I keep hearing is, well, how do I develop locally? So, there are some answers that you can give, that you can have in your back pocket ready to go. One approach would be run everything locally. So you can use Docker. You can Docker compose up. That's one possibility. You can just have ready the ability to execute all of your microservices locally. This may be a good solution for you. It may actually not be a good solution for you. As you scale up, as you go from dozens of services to hundreds of services, or maybe even thousands of services, you might outgrow this solution. So what else can you do? You can run just enough locally that you can test basic functionality. So you'll probably be organizing your developers into teams, and maybe those teams will run their services locally, but all the other services that are provided by all the other teams, you might still not run those locally, and then when you're ready to test interaction with those services, you can push to a dev cluster or push to a test cluster. Another possibility is continuously deploy to a dev cluster. So change your code, execute it locally to see that it does what you expect it to do, and then commit it, push it, and let it continuously deploy to a cluster dedicated to you. This is actually what I did at my last place. And it worked really well because everyone had their own dedicated cluster and they could see every service running. And they would have the production version of every service running that they weren't working on. And then they would have their branch continuously deployed that they were working on. And they could actually push their code and see how it all interacts. One other note here, there is Cloud9. I don't know, how many of you guys have ever used Cloud9? Yes, I've recently started using it, probably in the last 6 months. It's an online IDE. So instead of thinking about how do I develop locally, instead you move local into the cloud. And all of your development is done from the cloud first, And then you can check out code, run services locally, and you can even have them talk to your remote clusters and sort of, it's almost like they're a part of the remote cluster. So that's definitely an awesome option as well. So another one, deployments are painful. Will that get any worse? Well, I talk to companies all the time that tell me about their deployments that take hours. Sometimes it takes a day. Sometimes they think it's going to take hours, and it ends up taking a day because of all of the problems that come along. A deployment never happens the same way twice. It executes, it does what it's supposed to do, and then they have to go through and clean up all the things that it missed. So deployments tend to be problem areas. So when you talk to your developers or talk to your business people about increasing them, all they think is, well, I'm going to take that problem area and multiply it by 10 or by 100 or whatever, and that sounds like a bad idea. So have an answer ready for, will this get worse? No, we're going to streamline deployments, we're going to automate everything, and we're going to use tools that we'll have at our disposal to be able to eliminate the problems that we're seeing today and deploy in a totally different way. And we'll talk more about that in a second. My config management handles everything perfectly. I'm just going to bake in microservices into my config management. I see why it's tempting to do that. As operations people, you might be used to putting everything into config management, because that is the authoritative description of how a server should look, right? Well, the difference here is, with this move from Monolith to microservices, we also want to take advantage of not having to think in terms of servers. So we want to think in terms of services, and all we care about is having our service run and having the right scale for our service. We don't care what it runs on. We don't care where it runs. It just needs to be running. So if we start to pivot and think about services instead of servers, then we just need to be able to describe services. At that point, the server itself can become very simple. So I was actually able to get rid of config management altogether. What do you mean you have to be on call? With a shift from Monolith to microservices, there's going to be a lot more to know about. A lot more, instead of one monolith that everyone knows how to restart, you might have hundreds of services and one team of people, one operations staff. It would be very difficult to potentially impossible for them to know all the details about how the interactions and interoperabilities work. So put the development teams for those services on call, because they're the experts in that service. But of course, the resistance is, well, on call sounds terrible. I hear the operations team complaining all the time that they got thousands of pages over the weekend. They were up for 12 hours working on a problem, et cetera, et cetera. The answer to this is, we're going to fix that. On call is not going to be like that. If we can solve all of the basic problems of on-call, how to restart a service, how to make sure that it's running, how to make sure that it's healthy, if we can solve all of those problems, then the on-call becomes a lot better. And the problems that you might end up getting paged with at this point are going to be more developer-related. There's some code that isn't working quite right, so I need to change it and push a fix. And that's definitely something that a developer is going to be more likely to do. So how can AWS help with this? Well, I mentioned Cloud9. Definitely check that one out. There's also code build and code pipeline. So these will actually orchestrate actions for you, totally customizable. You can have them execute pretty much anything. We have Amazon ECS and EKS, and then of course AWS Fargate. And these will be really good tools for you to orchestrate your containers. So we're going to take a look in a little bit, and we're going to talk specifically about containers. How does Docker help with the migration? So anytime you talk about monolith to microservices, Docker is almost always part of the conversation. Why? Well, one reason, packaging. So if you think about all of the problems with distributing software, how do you know that you have all the libraries installed in all the right places? How do you know that a server didn't miss its check-in, didn't get an update? If you can bundle all of that together into one package and distribute it around in one form, then you can be guaranteed that you have everything you need to run this code, and then you know it's going to execute the same everywhere. So Docker solves that problem for us. So that's why it goes hand in hand with a switch from monolith to microservices. What about scaling? So with scaling, we can scale up, we can scale down. Because Docker is so easy to execute, and because it executes the same, no matter what language you're running, you can build tooling around, make more of these, or tooling around, okay, I don't need this many, knock some down. And that tooling becomes universal no matter what language it is you're running. Experimenting with, when you have all of these problems solved, packaging solved, distribution, how do I push an image around, and then scaling solved, then experimenting becomes easier. You can actually have a developer just have an idea, and they aren't bound by, I need to write in a certain language. They aren't bound by, I need to have an instance of a certain type, or certain resources, or certain libraries installed. They don't have to go to operations and say, make me a server that looks like this, and have all the back and forth while that happens. They can just experiment, package up their code, see that it runs, push it out to a test cluster, and then start to get people's opinion on it. They can show it to their product team, and they can say, what do you think about this? And then they can iterate on it, or maybe roll it back. Some companies that are very mature in this area already will actually push this all the way to production. And they'll actually send a small amount of traffic to production and get people's opinion on that. So how can AWS help with this? Well, of course, ECS, EKS, as we mentioned. There's also ECR for hosting your containers. This is a registry that you can use. It's very robust, very scalable, and something that you don't have to run yourself. CloudFormation, and then there's Application Load Balancer. Application Load Balancer, or ALB, is one way to actually route traffic where it needs to go. And you can route traffic in a very intelligent way. Then there's CloudWatch, Amazon or AWS Code Pipeline, again, for orchestrating whatever actions, whatever changes you need to execute, and code build. So, of course, the technical challenges. If we stop and think about what are some very common problems that we run into, problem number one is the service running? Is my monolith running? And if it's not running, what do I need to do? So operationally, for years, we've done things like, we'll start the service with supervisor D, or start the service with Monit. That's, of course, a great answer. But what if you have hundreds of services or thousands of services? Can you imagine trying to configure Monit for handling that, or having services that might be there or might not be there, or trying to scale up or down very rapidly, second by second? It's not really built for that, right? So orchestration can help us here. My clicker is sticking. Is the process healthy? This is another problem that it's a common problem, and we want to be able to solve it. So having a built-in way to health check, having a built-in standard way to define what a healthy process looks like, and then if it's not healthy, a standard reaction. The standard reaction is simply kill the container and let the orchestrator start up a new one. How do you get traffic into your processes? Again, standardize around something like ALB for ingress, NLB if you don't need layer 7, if you want layer 4. sending traffic to the right location, and have that location be what's dynamic. So as containers start up, spin down, run on random ports, you can actually have ALB and NLB have the orchestrator update its config in real time. So another one, how does one service find another? With a monolith, you don't really have this problem because all of the logic, all of the code is inside one monolith. So it's easy to just understand I'm going to call another function, I'm going to call another part of the code. But if that's actually now broken out and running potentially somewhere else on a different machine, how do you know how to find it? How do you address it? So service discovery is something that is built into many orchestrators, including ECS. We have integration with Route 53's service discovery, and EKS. We have built-in service discovery available. With that, we just give all of our services unique names, and then we can address them directly by the unique names, and we can route traffic from one service to another according to name. When should you scale up, or when should you scale down? Metrics are part of a native orchestrator. This is part of a healthy, robust orchestrator. So being able to understand what metrics should I be seeing when I'm healthy, when am I at my cap, and when do I need to scale up is something that you'll figure out for your own service, and then you'll be able to just sort of wire in. And when you reach a certain threshold, make more. And if you need then to have a bigger cluster, because your machines are so simple, you can simply just add more machines to your cluster. And then, of course, deploys. I mentioned this a minute ago as a pain point. So how does orchestration solve deploys? Well, this is one of my favorite parts. Orchestrators, they basically work by describing the end state. This is the state that I want to see. And then the orchestrator figures out, what do I need to go and change to make that happen? So you don't have to SSH to 1,000 servers. You don't have to execute remote commands or execute a script or execute a series of commands. You don't have to copy a bunch of files from one place to many and then move a bunch of symlinks and have all this coordinated effort. Instead, what you do is you just push a description or update a description, potentially with a new Docker tag. And then the orchestrator says, okay, well, everything as described is perfect except for this one Docker tag. So I'm going to go ahead and do whatever I need to do to push out images, have the agent running on each server, pull the right image, and then restart the process, restart the container. So it makes it very simple to do deploys, and it's in a unified sort of way. What else do we get out of using orchestration? By baking in all of our logic, all of our description of how our services should run into the orchestrator, then our machines, the description or the configuration of our machines becomes very simple. So it becomes very easy to rotate your machines out. So if you have any kind of security risk and you need to update, it's easy to just replace machines with newer versions of machines. And this actually leads to immutable infrastructure. And here immutable doesn't mean impossible to write to. It simply means I'm not going to mutate this config. I'm not going to go from change 1 to change 2 to change 3 to change 4. I'm going to start fresh every single time. And anytime I need to update a config, I'm going to update the config and then replace all the machines. So they will start with the updated config. What else can you do with orchestration? It can help save you money. So you can replace special snowflakes that are out there that have to be a little bit different. Replace them with running container that are just running inside your cluster, which is just a big resource pool. Docker will make it easy to co-locate services. So instead of one service, one instance, or for reliability, one service, 3 instances, you can actually just have a fleet of servers out there that is just a big resource pool, and you launch Docker containers until you're close to full. And as you need more resources, you simply add more instances, and then you can run more Docker containers. So how can AWS help with this? Of course, ECS, our native orchestrator, EKS, if you want an open source orchestrator, it's our open source Kubernetes service. Fargate, if you don't even want to manage instances at all, don't want to think about scaling the underlying infrastructure, you can execute on Fargate. CloudFormation for describing the end state of your infrastructure, and then CloudFormation will just reach out and make it happen. Autoscaling for scaling up and down your tasks or your containers, and then ALB for routing traffic, CloudWatch, and then Route 53 for service discovery. These are all definitely services you should be checking out. So next up, I want to introduce Max Blaze. He's the staff operations engineer at Duolingo, and he's going to talk to you a little bit about their experience breaking down the monolith to microservices.
Okay. Thank you, Brent. So I think Brent covered a lot of the social aspects, and we definitely ran into a lot of these things as we moved from monolith to microservices. I'm going to really get into the technical details. But before I do that, I want to take a poll. So how many of you have heard of Duolingo? Wow, most of the room. Do we have any really active users? Okay, a few more. So for those who don't know, the mission of Duolingo is free and accessible language education for all, and we really take this to heart. Let's go back. All right, so this is our main application. It is currently the most downloaded education app in the world, and what we really try to do is gamify learning. We want to make language education fun for everyone. And right now we have 30 languages across 80 different courses in various language directions. And one of the cool things is English is over 50% of our user base worldwide. So there's a great demand for learning English. And not only is it fun, it's very effective. So there was an independent study conducted a few years ago. 34 hours of Duolingo equals 1 college semester of Spanish. And we have a lot of users. We have 300 million worldwide. And we also have a very lean company. So we only have 150 employees, about half of which are engineers. So here's our growth curve in terms of users and employees. And I often get the question when I show this graph is, how are you able to sustain this sort of growth with so few people? I mean, we're thinking about 2 million users for every single employee. And the answer to that is A/B testing. So we make very specific choices on the sort of experiments we run, and we have hundreds of them running at any point in time. And as long as we get results that are statistically significant, those are the sorts of features that we push, and that's really helped us over the years. So here's a brief history of our infrastructure. We launched in late 2012. We were born on AWS. We've never run on anything else. And we launched with mostly Python 2 stack, running with mostly manually built infrastructure. So things got more complicated over the years, and we had to implement some sort of configuration management. We ended up going with Ansible, and we're finally able to rebuild all of our AMIs with a very definitive configuration. And some more time passed, and we started to run into this issue where deployments were not happening fast enough. Like I said, we're running lots of experiments. Developers want their changes out immediately all the time. I'm sure a lot of you have this issue. So we really started to think about microservices. Actually, our first microservice did not run on ECS. It ran on Beanstalk. And we gave developers access to the entire stack so that they can move really quickly. And that also became kind of an incubator for our microservice platform that we later moved to. Around the same time, we also started auto-scaling on EC2. We started to care about cost at this certain scale. Then we added centralized dashboards and logging. This was so that all of our development teams, as they were growing, can have a lot more introspection to what was going on for all these microservices, and also the monolith. And I would say Terraform has been one of the biggest wins, at least for me. This was life-changing. So at this point, we actually imported our entire manually built infrastructure, for the most part, and we were able to, for the first time, do code reviews of the infrastructure, which was absolutely fantastic. And then a little over a year ago, we started moving towards ECS and ported our first microservice there. So in general, why move to microservices? So there's scalability. So not only did we want to scale the infrastructure horizontally rather than vertically, we also wanted to scale our teams. So we didn't want to hire 1 or 2 engineers for every new service. Like that wasn't going to happen, especially with our size. So we really try to automate as much as possible. I also mentioned velocity before, so developers can deploy what they want, when they want. There was also a problem of flexibility. So developers wanted to start using more languages like Scala, Node.js, Python 3, rather than just our old Python 2 stack. And also reliability. We wanted to break away the really fragile parts of our monolith that weren't really important, that could impact reliability, and we wanted to achieve 4 nines. This was something we had never done before, or even 100% uptime. We were also running into some cost savings issues at this scale about a year ago, and we really wanted to start tackling that, especially with compute. So what do you decide what to carve out of your monolith first? So this is what I recommend. So start with something small but impactful. So one of the first features we carved out was just simply reminder service. It's just a reminder to practice your language in Duolingo. And then we moved up in size and complexity. So I swear with every single feature we ported, every microservice that we moved from Beanstalk to ECS, we ran into some unexpected problem. I swear every single time. So accumulate all that knowledge and then tackle the really hard stuff at the very end, and it'll be much easier. Now let's talk about just raw probabilities. So let's say you have 2 nines of availability across your monolith. It's not great, but it's OK for something that's not that important. And you split up your features, but they're still intertwined. They're still dependent on each other. Your availability is going to go down. You're not really at least going to be solving the problem of availability. You might solve, flexibility or velocity, but yeah, your availability is not going to be great. Versus if you make them independent, if you implement something like circuit breakers, there's a lot of open source tools like Netflix Hystrix. Since we were on Python, for the most part, we actually implemented our own circuit breaker library. You can get something like 6 nines of uptime with just 3 services, right? So why use Docker? Brent touched on some of this before. So it standardizes the build process and encapsulates dependencies. Deployments are really quick. Rollbacks are really quick. So you're spinning up Docker containers in seconds rather than minutes with instances. And one of the best things for us was the flexible resource allocation. So you have essentially an infinite combinations of memory and CPU to fit your microservice rather than trying to pick an instance that will fit it. And also, one of the biggest early wins that we had was simplifying local development setup. So this was our initial setup, right? Just like a long list. Please don't screenshot it. It's not useful. But at this point, when we were doing this, we had dozens of microservices across lots of teams. And every new employee had to come in and go through this entire process, which would take a long time. And I should also mention that we were running on macOS. So our operating system was not running the Linux it was not matching the Linux platform that we were running in production, which can be an issue. So we went from this running on macOS, and with Docker, it turned into this. So now we have a standard way to set up local environments, which is nice and easy. So why use Docker with Amazon ECS? So we looked at a lot of different orchestration platforms. We looked at Kubernetes. We looked at HashiCorp Nomad. And they were all missing at least one of these features. So we ended up going with ECS. So there's task autoscaling. So if you're not familiar with this term, a task is a group of one or more containers that are grouped, and that is a task. So you can scale those up with CPU across the entire service. There's task level AWS IAM. So we can isolate IAM permissions at the service level rather than at the instance level. There's CloudWatch integration. We were already using tools like Grafana, so this plugged right into our existing monitoring infrastructure. And also dynamic ALB targets. So what do you do with this random port that you're assigned to your container? You have to map it to something, and ALB integration makes that really nice and easy. It's essentially automatic. And also manageability. Like I said, we're really small. We only have 2 ops engineers in the entire company. So we didn't really have to manage much. We didn't have to worry about the Kubernetes cluster or the Nomad cluster going down. It was all managed for us. So like I said, we're huge fans of Terraform, and we actually use Terraform to abstract all of this for our developers. So we have a simple web service. You could stick, a WAF or CloudFront in front of this. We have a worker service, either daemonized or cron-based, using CloudWatch events. We have a multitude of data stores, so if you need encrypted passwords, you could use KMS, Amazon RDS, Aurora, Dynamo. We're one of the biggest users of DynamoDB, and also we use Redis and Memcache quite a bit. It also tied into our existing monitoring infrastructure. So all those tools I showed at the beginning, we're still using every single one of those. We just made small incremental improvements until we reached this current setup here. So let's take a look at what one of these services looks like in code. You can see it's very small number of parameters. So the first set all ties into billing. So these are all billing tags. These are all mandatory for every single service that we deploy. You have an auto-scaling set, so the min and max count, CPU and memory resources, and at the bottom there you can see the container port, which will map to the ALB. So here's what one of those definitions looks like for an Aurora database. Very similar billing tags, so you could see billing across all the microservice and all of its resources. We have the database engine, so we're running Aurora Postgres, and also the instance type here. You should also notice that there's a KMS key that's fully encrypted. So this is what our CICD setup looks like. So we use Jenkins for building the Docker files, and there's a developer cycle there, and we use GitHub. So the custom thing there is the plan and apply while supplying a version string. I should also mention that we use Amazon S3 to store the Terraform state in an encrypted bucket. So that allows us to have passwords within Terraform without actually uploading it to the GitHub repo. So the normal flow is the Docker file is built on Jenkins. It's uploaded to the Amazon ECR repo. And then ECS pulls down the image during the deployment with Terraform. So let's talk a little bit about load balancing. So this is one of the first bumps that we ran into. So ALBs and CLBs are not equivalent. And they're not. The ALB is definitely not a drop-in replacement. So the CLB, if you're not aware, aka ELB, that was the old name of it. ALB runs at layer 7. The CLB can run at layer 4. It can do TCP. And ALBs, we found, are definitely more strict when handling malform requests. So we had some services that formed their own requests and had custom headers. And the other thing to keep in mind is the ALBs default to HTTP2. And one of the interesting things about that is headers are always passed as lowercase, and we had some services that assumed a case. So you could see that becomes a real issue. So there's some little things you have to think about. There's also lots of differences in the CloudWatch metrics. So ALBs are more discrete for errors versus CLBs are continuous, and this can kind of mess up your alarms if you're not careful. So task level AWS IAM permissions. So I definitely advise you to apply all of your IAM permissions at the service level. don't really share any IAM resources. I know there's kind of a big push to do that sort of thing, but keep everything separate because you don't want a small accidental change to ripple across all of your services. And one thing to note, IAM task level permissions needs to be supported by your AWS client library. So we have a lot of Bodo 2 code in our Python stack, and it actually doesn't support this. So as we're porting to Bodo 3, which does, we've actually moved all those applications to a separate cluster to kind of segregate it. So microservice standardization. So this becomes a really big deal as you add services. And I wouldn't even run a dozen microservices without some sort of standardization. So from the get-go, try to develop a common naming scheme for repos and services. Auto-generate as much as the initial service as possible. So have some sort of service factory so your developers can start with something nice and easy. The third point is so important. So move core functionality to shared libraries, especially any access to Amazon APIs. You don't want every team implementing those API calls separately, and then at some point you want to standardize everything, and then you have to accumulate all those. It's a pain. Do it from the get-go. Definitely provide standard alarms and dashboards, and I'll show you what those look like at Duolingo. And also periodically review microservices for consistency and quality. We don't do this very often, but I'll show you what we do for that. So this is what one of our web service dashboards looks like. At the top, we have local time and UTC. This becomes really important when you're looking at various console dashboards. They may be in your local time zone or UTC. Your logs might be in different time zones. You might have some other third-party applications. So that's really nice and handy. So for whatever dashboard that you just happen to be looking at, you'll always have that reference. So we have ECS things like healthy, unhealthy, and running tasks. We have customer-facing metrics such as latency, average, and percentiles, number of requests, CPU, min, average, max. And one thing you should always do is divide as much as you can by AZ. So this might help you detect a bad instance or a bad container that's maybe running out of memory on an instance. And here's what our worker service dashboard looks like. It's a lot simpler. We simply add an SQS dashboard at the bottom for visible and deleted messages. And we also integrate all of this into PageRudy. So like Brent mentioned, we actually have each one of our service teams on call for their own applications. And that's another reason why you really want to have standardized dashboards. So they can be on call for each other's services. If you have people moving teams, it's nice and easy to onboard. And our integration has 2 levels of metrics. So we have emergency alarms, which go to PagerDuty. And then we have warning alarms that just go to email. It might be a team mailing list, for instance. We also include links to playbooks. So if you're not that familiar with the service that you're on call for, you can quickly reference the playbooks there. And we're big users of Slack. So everything, including alarms, PagerDuty alerts, deployments, they're all visible in Slack if you want to see them. So I'm going to come back to standardization. So we gamify learning, so we decided to gamify the grading of our microservices. So we have lots of different categories here and different levels. So we have bronze, silver, gold, and platinum. And if a service internally is getting all platinum, it's really, really good. That's just the defining service within the company. So this is what part of the grading rubric looks like. We try to automate this grading as much as possible. So one of the things you can automate is there like a README file, or is there an owner that you can easily automate that. Some things where you might have to bring a bunch of people in a conference room and take a look at the code is like, is the architecture explained well? If you have some machine learning that can do this, let me know afterwards, please. All right, so this is one of my favorite topics. This is what we've been working on over the last quarter. is cost reduction. So there's essentially 2 ways that you can save costs using ECS. So one is at the cluster level, so you can change the instance type, pricing options, so spot, RI, on demand. You could auto-scale the cluster, or you could add or remove AZs. So not all AZs are created equal. Some AZs have access to more instances than others, and this can be a big problem at a certain scale. So the other way you can do that is by allocating the right amount of resources for each service, and also using task auto-scaling for each of those services. So roughly a year ago, when we first set up the ECS cluster, this was our starting point. And our favorite instance type was a C3 2x large. We also had some reserved instances, and then the rest we used on demand. And I should also mention that we were not auto-scaling at the time. We didn't want to add that complexity at first. So roughly, 6 or 7 months ago, the C5D came out, which was super exciting for us. And you notice we skipped C4. That's because we like to use lots of ephemeral storage. We have lots and lots of logs that go through our elk stack, and that's kind of where they buffer. So if you take a look at the math on this, the C5 is actually 50% faster than C3. So that's a huge win right out of the gate, and it's cheaper. So it's win-win, right? Well, there was a slight problem. ECS uses core to define the amount of CPU. So cores are not really equivalent across machine types, right? So C5 is 50% faster than the C3, so you're going to have scaling issues. The units are just not equivalent. And what we actually found was that services were not scaling up when they should have been, and some of them were actually running out of threads. So this is a huge problem. So like I said it before, now we're on C5D. Again, we have reserved instances and on demand, and we're not scaling. And this is where we wanted to end up. We wanted to auto-scale. We wanted to use the entire range of C5D and M5D so we can grab as many instances as we possibly can and bin pack them. And we also wanted to use Spot. We wanted to get that 90% savings. And we ended up going with this product called SpotInst. And I'll tell you a little bit about that. So here are some of the features. We were able to mix the families and sizes of instances like we wanted. We could use all of our RIs that we had before any spot was used. They also gave us a 15-minute notice. If you just use Spot Fleet, for instance, you only get a 2-minute notice before an instance shuts down. And what was really cool is they fit the capacity, the different instances and sizes, to your ECS task load. So it's kind of like a reverse bin packing. And they also provide this really cool AZ capacity heat map. So here you're seeing US1E doesn't have all the instance types that we need, so we would simply remove that AZ from the cluster entirely. It also has some more ECS integration, so it will drain all the tasks for us. We could also provide some cluster headroom, so just adds a little bit of a safety buffer in case we have a spike in traffic. It allows us to spread capacities across AZs, and it bills on a percentage of savings. So if we're not using the service, we don't have to pay anything. And finally, it has Terraform support, so it could fit into our existing Terraform modules. So this is what one of our smaller clusters looks like. Purple is reserved, green is Spot, and you could barely see it. The blue line is on demand, so we're actually saving on quite a bit of money here. And we're at a 50-50 ratio, so 50-50 Spot, and then the other 50% is RI, or on demand. So let's talk about microservice cost at the task level now. So what I advise you to do is to audit every single service, make sure they're not allocating a ton of CPU and memory. And internally, we have these goals here. So 60% CPU, scaling factor, and also we try to add a little bit of a buffer for memory, so 60 to 80% of memory. So you could kind of eyeball the graph and kind of come up with a CPU unit, but there's definitely a more direct way to do it, much easier way to do it. So you take your allocated CPU that you have, so that's the CPU core units, you multiply that by your current utilization from the graph, and then that gives you what you're actually using in the ECS CPU units. You then take that, and then you simply divide it by the desired utilization, and that's what you set. So that's how you get the auto-scaling threshold. And then for memory, we simply just track memory usage between deployments, and we take a look at the graph. If it's ever increasing, you know you have a memory leak that you have to fix. If you have memory leaks that are really hard to fix, definitely set containers to restart if memory exceeds 100%. You don't want tasks knocking out other tasks in the same instance and causing cascading failures. That's really bad. So don't over-allocate memory. I know the option is there, but don't do it. So one other note on cost. So we were actually spending quite a bit of money on S3 across all of our services. And it's a storage service, right? So that's what you should probably focus on. Well, not always. So we spent a lot of time looking at how much data we're actually storing, which is in the dark blue or purple at the bottom. And you could see we kind of got the cost down, but the overall cost was still increasing. And we found this is really strange. So we split up the cost by API call, and we found out that list all my buckets plus get object were over 50% of our Amazon S3 cost, which was pretty surprising. And we actually went in the CloudTrail logs and found it was a single service causing all of this havoc on our bills. So keep that in mind. All right, so overall, we reduced our compute cost by 60% by using Spotinst. We reduced our cost per MAU by 30%. And we also brought our entire AWS bill through some other cost savings routines to 25%. So you can see from August, before we started putting all this into place, to October, it's a huge drop there. So key results. So scalability. We now manage over 100 microservices. Teams can deploy their own services when they want. We now have the flexibility to support 3 different programming languages. So we added Python 3, Scala, and Java. We actually hit 4 nines of uptime last quarter, which was the first time ever in our history. And we also reduced our cost by 60%. So if you enjoyed this talk, we're hiring. We're actually not in Silicon Valley. We're in Pittsburgh, Pennsylvania. And it is definitely not the smoky image that you have in your head. It's actually become a really booming tech town with lots of great food. Just FYI, so check this out. So here's the slide for your cameras. These are some really great resources that helped us along the way. So Sam Newman's book, Building Microservices, is what I consider the de facto standard microservice book. Susan Fowler's book is also really great. It covers more of the operational level. And then I have some other links here that we use every day. So thank you.